volunteers by now. Being public
I bet not.
Exactly.
All right, I'll sort these around.
Wonderful. Have some remote attendees as well. Yeah, we have remote attendees. We want to make sure we look into see whether someone is raising their hand. So I'll try to do that.
Is it time?
It is time, actually.
Okay, let's go ahead and get started. Okay, I sent a note to the mailing list asking for minute takers and JavaScribes. I got volunteers for neither of those, and we're not going to begin until I do. Okay, thank you, Charlie. Charlie said he would take minutes. We're still looking for a JavaScribe. Thank you. Okay, slide it. As with all the meetings here, the note well is on the screen. If you're not willing to follow these rules, please leave the room. So we just filled in the 2 question marks. The documents are on the data tracker. We have a mailing list, and the blue sheets are going around. So I'm going to let Carlos take a few minutes to talk about the success criteria, and then we're going to talk about the problem space, and then we're going to have some discussion about whether the IETF is the right place to do that work, whether we need relationships with other SDOs, mobility in connected rail. Yes?
Is there a working Java room? I just tried to get into ITS and it doesn't work.
Oh boy. I'll send mail as soon as I'm through with this slide and find out what's going on. And then we're going to talk about a proposed charter and figure out what to do next. Over to you.
Sure. So we wanted to flash from RFC 2418 the success criteria for Evolve and some of the usual outcomes of a Birds of a Feather meeting. I'm not gonna, read that, but we did want it to, show that so that we're all aligned and on the same page on what success means for us. And this is an opportunity for us to gauge interest on the topic. It's an opportunity to understand not only if there's interest in the topic, but there's interested people to actually work and share cycles to produce outcomes on the topic. And last but certainly not least, as Ross just mentioned, whether the IETF is the right place for channeling that energy as well as that interest. So the goal of today is to get a sense of that interest, energy, and applicability to the IETF, which we don't necessarily need to do now. That may result in additional discussion on the list, but that's the goal of our meeting. By the way, we have a fairly packed agenda, structure as Russ scheduled, as Russ just mentioned. So we can actually get on with the first presentation.
Presenters, remember to stand at the pink box.
Hello, my name is Alex Petrescu. My presentation is a tutorial on IP in vehicular communications, but last minute I wanted to add this Category A liaison letter that has been recently established between IETF and ISO TC 204. Russ Housley is the shepherd of this activity. So now going back to the main topic, we have 20 minutes on a tutorial of IP in vehicular communication. I hope it is enough time to present everything. You will see it is organized a little bit different than your typical tutorials of vehicular communications, because this is mainly about IP. First, what kind of link layers do we use in vehicular communications? Let me present an example. This is a link layer called DSRC for Dedicated Short-Range Communication Systems, which exchange these basic safety messages. These are messages that need to be exchanged between vehicles, BSM. And they have, when creating or communicating these messages, there are very stringent requirements, for example, related to accuracy. They would like the two-dimensional position to be within a 1.5 meters maximal elevation difference between low and high to be with a detail of 3 meters, speed within 1 kilometer per hour, and so on and so forth. You will see some of these requirements are typically physical movement requirements, and they are somehow available in open sky conditions. That means mainly localization with based on satellite signals. So this is a typical message that is exchanged on a typical link layer used in vehicular communications. There are also requirements with respect to congestion control, because we don't want this message to get lost because of other BSM messages. But that is the link layer part. At IETF, typically one does not design link layers, okay? The question now is, how about IP? Where is IP in this picture? How is IP arriving in vehicles? So here are some answers. I prepared 4 answers for you that I see in the work I do with particular prototypes. The number 1 module that brings IP in the vehicle is the built-in cellular module, okay? Many cars in the market today are connected with the internet with a cellular module or cellular interface, if you wish. That brings it live road traffic data, map information, weather, software updates, very important, and recently car-specific applications store. Many car manufacturers provide their own application stores these days. The second one is a user smartphone. You come with your smartphone in the car, you link your smartphone to the car with a technology like mirror link, for example, there are multiple, and then you connect the car to the internet by using your smartphone. And it's not all. Nowadays, more specifically in February this year, you have announcements with aftermarket OBD2 docked Wi-Fi hotspots. OBD2 is a socket in every car. So you have now, for example, Samsung Connect Auto, which sells a device that transforms your car into a Wi-Fi hotspot, even though initially that car was not connected to the internet. And finally, a DSRC, or in Europe, EU ITS G5 box for specific applications, like for today's V2V use cases or today's V2I interactions. In the future, you may expect LTE V2X 5G connection boxes and even more application-specific boxes, each one of them being IP-enabled. So that's how IP arrives in the automobiles today, and we need to consider all of them if we consider IP. That's about inside an automobile. How about the outside? Again, the situation today, you'll see here a very small blue point, which is actually a car. So we consider what's the communication outside of the car. Typically, multiple sensor networks, multiple sensor devices are deployed in the car that try to sense what's happening outside. And this is what I call bounce sensors, because they use this principle of the radar, or what we call bouncing principle here. You have the car in the middle, sends a signal to some obstacle, which could be a front car, measures time, and then realizes how far the front obstacle by hearing the bouncing signal. The same for rear. You'll see there are multiple kinds of sensor. You have for the rear of the car normally ultrasound, but for the front car, for the front of the car, there are long-range radars, mid-range radars, and short-range radars. And also some cars use some sensors for above of the car. Maybe in the future when drones will be used to be docked on the car. So the current applications are assisted parking, enhanced rear view, dead angle detection, enhanced cruise control, emergency braking to avoid vulnerable road users, and more. These are the kinds of applications that are realized by using this bouncing principle and multiple radars, multiple sensors deployed in the car. Of course, this has drawbacks. If any one of you has such a car for private use, then one is supposed to read the user's manual. I will show it separately. This depends a lot on the propagation patterns of these bouncing radars, and it is very hard at intersections. There are too many sensors, and outrageously ignores the other car's intentions. Okay, if I can set my own speed based on the front car, but the front car may not like that the rear car follows it. Okay, this is the don't follow me. Maybe I don't want all cars to follow me. That's the current situation. What do we expect in the future? We expect to have the message exchange principle to replace or come in complementary to the bouncing principle. That means the car will send messages to the front car or the rear car, and there will be a request-response kind of interaction, okay? For example, a request could be, what is the position of the front car? And the front car will reply, this is my position. Can I follow you? Yes, you can follow me, or no, you cannot follow me for privacy reasons. Same for the rear obstacle and so on. If this is done, if message exchange principle is used instead of, or in complementary with bouncing principle, then new applications become possible. Smoother, longer authorized platooning is possible. Mirrors at intersection, virtual siren application for ambulances, see-through trucks, and more. Actually, sky is the limit in the kinds of application. And I will show you on this slide. Not sure how much visible is it, but please download the slides. These are a few current prototypes where IP is used between vehicles. The Samsung safety truck starts with the observation that in Argentina,
The ITS
In
Jabber room
Argentina,
is now
one
live.
person, excuse me. Yeah. In Argentina, one person dies in traffic accident every day. Okay, that's the observation. What Samsung Safety Track is doing is proposing to put a webcam in front of the car. Webcam, okay, that's an IP-enabled camera. And to display in the rear of the truck what the front camera sees. So this image displays what me behind the car I see in front of the car, so I know not to take over if there is another car coming by. This is an application demonstrated late last year and featured on YouTube, and that uses IP inside the truck, but this image in other prototypes is also streamed by the front car to the rear car. Okay, this is currently prototyped. DAF and TNO, two organizations in Europe, demonstrate eco-twin, two trucks following each other. And in the small announcement here, you will see they say they use Wi-Fi to communicate between the two trucks. Multiple companies in America as well also consider platooning trucks for vehicle-to-vehicle communication. This is a virtual siren, an application on a smartphone to which a ambulance tells where it is coming from, so you know to make place. This is in Japan, an intersection where the traffic light pole identifies the vulnerable road users and communicates this information to the cars passing by with IP. Okay, so this is how prototypes today are using IP outside the vehicle. That's about experimentation. Let's see now what's happening at SDOs. Okay, typically we wonder which SDOs consider the use of IP, and there are a list of such standards development organizations. This is extracted from DSRC with permission. It pictures here a MAC layer from IEEE and the Phi plus MAC features also from IEEE. And very important, right above it, a DSRC wave short message protocol and WSA 1609.3. Okay, this is currently what's being developed, debated, and standardized at IEEE. But at the same time, you'll see side by side with it a orange IPv6 there with TCP/UDP and some non-safety applications. Okay, so that means IPv6 is there. DSRC does consider IPv6, but for non-safety applications. That's for DSRC standard. But you also have similar in ISO-CALM, HCTC ITS, ITU. These are three major standards development organizations in the telecommunications sector and in the vehicular communications. I can talk about each one of these, but each one of these three also consider IPv6. Which teaches us that we need to, the IPv6 layer needs to cohabit, to live together with other networking layers if it is to be used in vehicular communications. Please read this slide on the slide set. There is more background on the US DSRC, very important for V2V, V2X. This is the range of frequency. I will show later there are some problems in the spectrum sharing at this place that DSRC and US considers. But that's only about DSRC. That only talks how DSRC is used in vehicle. If you go to ITU, which is the International Telecommunication Union, you will see flavors of DSRC that are considered in ETSI, ETSI European standards, ARIB in Japan, TTA in Korea. Well, it's too small to be written, but each one of those works on a different frequency range, okay? So you can imagine very well that a car built to be sold in America, here in IEEE, will not be able to talk to a car sold in Japan at Phi layer, I mean, at the Phi layer, because their frequency ranges overlap or sometimes are totally different. That's for the frequency. Now, for the modulation scheme, the situation comes to be a little bit closer to each other. For example, in Japan, In Japan, there are 3 modulation schemes that are also present in America, but there is a 4th modulation scheme not present in America, and that is present in IEEE and not present in Japan. That means that under certain situation, one can take a Japanese equipment and tune it to be able to talk to a US vehicle at the Phi and Mach layer under certain conditions, certain uses of the frequency of the Mach. That may be made to work at Phi and Mach layer, but the problem is that each one of these standards also comes with its own application layer, with its own messages to be exchanged. For example, at CETSI, you have CAMDNM messages, but in the US, you have BSM messages, or they are not interoperable. Okay, you cannot, if you send a BSM message to a car that only understands CAM messages, they will not understand. That's why you need an IP layer on top of them, and IP will make sure that above it is also TCP, UDP, and so on, and applications will be more interoperable. That's why applications that are developed for a TCP IP environment will be continuing to work even on this kind of layers that are interoperable only under certain situations. So the reference of these 2 tables is a IQR document. I can send separately if needed. And the message I wanted to convey is that only IP runs on that many Phi and Max. This is a discussion in the DSRC band plan. I'm relaying it with permission of John Kenney. In DSRC, there are multiple channels, 172, 178, and so on until 184. These are a little bit like the channels that we know in Wi-Fi, channel from 1 to 18. Now, there is a problem is that there may be some interference in this space from the wireless LAN 5.4 or from other equipments, not only from wireless LAN, but from other equipments that are for other activities. So there is a problem of dedicating each channel to certain applications. This looks strange to people who know that applications run very high above IP. But the current situation is that they dedicate particular channels to particular application, for example, safety application, control application, application services. So IP is allowed only on some of these channels, and this is being discussed. Of course, there is some opinion to be had on this, but currently that is the situation and could be discussed further. I will finish this band plan, go to what does this mean in terms of, this is my last slide of the tutorial. In terms of topology, okay, now think only IP. It's a little bit shown here. You have one vehicle that needs to communicate with another vehicle. What is particular about IP networks in this? Well, there are 2 things. First is that the link between the 2 vehicles is wireless. So this is a fragile connection. Vehicles move with respect to each other or move together, but this is the point where the connection may break, okay, between the vehicles, the wireless aspect, okay, it is here. This is why I call it fragile. That's the first aspect. The second aspect is that inside each car, you have a network that, contrary to the outside, it is very stable. Typically, you have Ethernet cables inside each car. So there is no problem of connection, or there is less problem of connection loss or of connection reestablishment needs and so on. And why? Because there is a car frame or a shield around the car. You have this shield that isolates very well the inside car from the outside of the car. So this creates the topology on which IP needs to have some particular way of functioning. For example, inside the car, typical IP that you have with neighbor discovery or TCP IP between entities in the car works very well, and also in the other car. Communication between my smartphone in my car to the tablet in the nearby car is not possible directly, because of the car shield. On another hand, communication between antennas of the two cars is possible, but is fragile. So this is what I call IP hop. The topology looks like a star topology because several cars may be near each other. We have a question mark on the star because, well, star would assume there is somebody in the middle, like hub and spoke. But here we don't have hub. So it's a star, more a star topology without a center. The center is, well, it's the 802.11p link, which is one IP subnet. So this ends the last slide. Yep, thank you. Thanks, acknowledgements. Okay, I couldn't have prepared this without the help from those two persons, John and Michelle. Thank you.
Excuse me, Randall Gallens. I had a question on the, a couple slides ago, you mentioned that IP, yeah, I think it was this slide. You mentioned because there's all these different standards for the lower level, the physical layer communications, and each of them use their own messaging layers, you want to have IP for interoperability. And so my question is, does IP really give you interoperability in this scenario? Because of the fact that if different vehicles are using different physical layers, different MAC layers, then they can't communicate with each other.
Yes, so if we talk DSRC only, or if we talk this 802.11p space, there are some overlapping conditions in the frequency range or in the channel numbers, and overlapping between the modulation schemes. For example, between IEEE and ARIB, if you look at the MAC, the two modulation schemes used here, there are 4 modulation schemes here and 3 modulation schemes. The 3 modulation schemes that are here are the same as the ones here. So if a Japanese car uses any one of these 3 modulation schemes, it will be able to talk to the American car here using one of these 3. But if the American car uses this 64 QAM OFDM, then the ARIB car, the Japanese, will not be able to understand. So there are conditions into which those two cars, even though they use different standards, are able to talk to each other at MAC layer. But their messages, their application messages, the ARIB message, will not be understood by the IEEE receiver. Whereas if it were IP, if it were like, I don't know, HTML page, then the HTML page could be understood if it was run on TCP over IP and over these. Is this clear or was I too long?
So you're saying that if you use IP as the messaging layer instead of the individual messaging layers, then because of the overlap at the physical layer, you could communicate.
Yeah.
Okay.
Yeah. Thank you.
All right, go to the, I think the second to last slide. Oh, the pic, yeah, that one. So that's clearly a very simplified topology because, I mean, if I understand this, there's going to be a lot of cars and they're going to all have the capability of talking to each other. So it's like almost a mesh, a moving mesh of cars that some see each other and then there's the groups behind it. It's actually a very complicated dynamic topology.
Yes. The dynamic topologies of the dynamic mesh topologies are indeed a concern that could be considered in the future. But if there is work to be done, I propose, or there is a proposal to work on simpler aspects of the mesh networks, okay? Only the communication between nearby cars, not very remote cars. And there are needs for communication for cars that follow each other or that are on line of sight of the driver and or between the car and the immediate infrastructure. But the mesh aspect is maybe too complex to consider at this time, maybe in a future situation. If the first step is built correctly, then maybe it could be scalable. That's one of the properties of IP, right? It's scalable, it's interoperable. So if the first building block is scalable, maybe it will scale in the future.
This is Dapeng Liu. So just a quick response to the previous question. So in some some chipset can support multiple different PHY and MACs. So in this case, if you use IP and you develop your application above IP, you can have the advantage that you can, have a single application layer that can run on top of different PHY and MAC. Thanks.
Yeah.
Yeah, Pat Taylor, Broadcom. I want to say a modulation scheme is not a MAC and a PHY. A modulation scheme isn't a MAC at all. And just because you have two things that use the same modulation scheme doesn't mean they can talk to each other, even if you then put IP above their MACs.
Yeah.
Because they're different MACs and they're different PHY encodings potentially within above the modulation schemes. So I don't think you just magically make them use IP above their MACs and they talk to each other.
Yeah. Modulation is just an example, and these standards are described by more than just modulation schemes. There is frame error correction, data transmission rate, many duplex methods, the TDD, CDA, and all these. These are aspects that are particular to the MAC and PHY, and to which I'm not an expert to answer. So I'm trying to say that this looks also a lot like what the smartphone can do. Okay, dual band, three band, quad band, pentaband, all these smartphones, okay, but they all use IP, right? So in the beginning, they tried to have WAP, wireless application protocol, to run on specific modulation schemes, but now WAP has disappeared, and you have IP on each one of these modulation schemes. But yes, I agree with the comment.
Eric, not Mark, if you can go back to the picture with the two cars. So my question is whether people have thought about what IP addressing will look like in this case. You can see that inside the car, sure, you will have some stable IP addresses, right? KCD6, ULAs, whatever, right? But how you actually set up IP addressing for these hubs, is someone already working on that? Or, because that seems like, I mean, conceptually what the car behind might want to do is just send something to the car in front and get something back. But the car in front is not an IP address, right?
May have one IP address.
Yeah, but
it's not
how does it know what the IP address is of the car in front?
That's
What's
a problem.
the subnet for that thing? If you're gonna route it from one of the hosts and it gets routed over there, you need to have a route for it too. So my high level question is, are people already working on this somewhere else? Or is this something that you think we should do in the IETF?
So the question to me?
Yeah.
Well, if you ask me, yes.
What? Is someone already working on it somewhere else?
Yeah.
Or should we do it here? Either or.
I mean, there are multiple groups of people at various organizations and standards development organizations and various organizations that work on these kinds of topics and that work, if I can say, separately, if you wish.
Yeah.
And the reason I talked about it at IETF is because I think at IETF there is this skill set that knows how IP works and what is needed. So how IP can be used in these kinds of environments.
Alex, just to be clear, are people in other places working on the IP addressing schemes for such a topology or not? Like yes, no?
Yes. ISO TC204.
And I'm going to cut the mic after people standing up right now.
This is Dino. I think what we see here is an IP mobility problem, so it needs to be in the IETF.
Hi, my name is Kutscher. I wanted to follow up a bit on Eric's question. So trying to understand a bit better the merits and also challenges for using IP in this car-to-car scenario. I mean, so you mentioned earlier it's primarily a one-hop communication scenario. And I mean, isn't that using broadcast anyway? And isn't the actual standardization challenge more like on the semantic layer, so like agreeing on the messages that you actually exchange?
No, there are multiple layers that need to be addressed. The application layer, agreeing on some message format, yes, is one of the important things. But there is also questions of congestion control or of what the lower layers do, what the upper layers do, session establishment, all these things should be considered, but it's not as easy as just considering that there is a broadcast between vehicles, because I'm saying one hop between, between vehicles, but inside each vehicles, there may be multiple hops, okay? Prototypes of current vehicles use multiple hops inside the car, at least 2 hops inside the vehicle. So you end up with multiple hops from one car to the other, but with one hop being the one that is fragile, that generates the dynamicity or the need of particular treatment, if you want. This is why it's pictured this way. And so semantics, yes, semantics of message exchange. Broadcast, yes, it's a broadcast media. It's a wireless, so anything wireless is broadcast. There may be some directivity in these broadcasts, like antennas may be omnidirectional, more directional than others, like sensors. But broadcast, no IPv4 broadcast, more IPv6 multicast. So this is the broadcast. This is the broadcast question, or?
Yeah, kind of. I just want to understand what the idea is there.
Yeah. So in the CACC presentation, I'll show more about broadcasts and scalability. Broadcast doesn't scale for IP.
Hi, this is Michelle Bertarvel from FB Consulting. I just wanted to highlight that this is an IP mobility problem, but we have to consider very severe constraint in the sense that the cars may be moving very fast, and you need to have device-to-device communication in some of the use cases. So it's just a comment.
Yes, device-to-device communications are without assistance of infrastructure.
This is Dino. If this wasn't an IP mobility problem, we still have different links that are not compatible, as you discussed. If you go back 30 or 40 years, we had these things called LANs. And I remember there was 2 forms of Ethernet, a token ring network, an FDDI network. And people tried building layer 2 devices to connect them together, and it was a mess. What made them all work was IP. So this is no different.
I fully agree here. Yeah. So next presentation, please. I don't know. Okay. So we wrote a draft with a few co-authors, James Huang, Thierry Ernst, Rex Budenberg, retired, and Charles Perkins. We needed to identify a particular use case that exposes this need of communication direct between vehicles, the vehicle-to-vehicle communication. So we identified, there are a huge number of applications that use vehicle-to-vehicle communication capability. We have selected these 2 ones, CACC and platooning, and I'm trying to explain what they are. First, a definition of the theoretical definition. Cooperative adaptive cruise control is combination of automated speed control with a cooperative element such as V2V and I2V. This is a definition from the PATH project in California at Berkeley. But in the draft, we understand CACC as automated formation of chains of automobiles following each other at constant speed, which is again an ideal definition that we tend to realize. So where is this coming from? Well, CACC, it's ETSI, ITS term, but if you want to buy a car today and you want to ask for a feature, okay, you will ask for cruise control. Everybody knows what is cruise control. In the last 1 or 2 years, you have now dynamic cruise control at the BMW. Okay, dynamic cruise control means that you follow the car in front of you and you keep your distance to it constant. If it accelerates, you will accelerate. If it brakes, you will brake automatically. So that's what's on the market today. And you may wonder what comes after dynamic cruise control. You will see. That's one car manufacturer, BMW. At Renault in France, it's not called dynamic cruise control, it's called adaptive cruise control. It does the same thing, and you wonder what's coming after adaptive cruise control. So why there is something after this means of cruise control is because currently the user manual of adaptive cruise control says that in a complex environment, for example, under or in a metal bridge, think Golden Gate or some bridge in New York, that's a metal bridge, the system may be affected, okay? So there is clear acknowledgement that this may not work very well in such an environment. So one may wonder why. We know because the bouncing system and these fading effects and so on. So they propose, actually the industry proposes to use this CACC, cooperative adaptive cruise control, in which a neighbor senses another neighbor, a car senses another car, and then it asks it, for example, what is your IP address? This is very simple illustration of the situation, because there is much in sensing and there is much in this your here, because you must know, you identify somehow the license plate of the car in front or of the car in back or the color of the car. You know a little bit the situation of, so you ask for an IP address and you get a response of the IP address to which you can communicate. So at this point, the car knows what is the IP address in front. And then you can also ask what is the position, speed, and heading, and then you can get a reply from the car. This is my position, speed, and heading. So you can decide whether you or you accelerate. So that's a sort of more advanced cruise control that has more capabilities and that is not subject to these metal bridge risks. But there are more questions like that you can formulate. For example, can I follow you? Can my car follow you? Do you agree? Or maybe you don't agree because you don't like to be followed. So, and also, can I follow you? And then the front response can be, yes, you can follow me, but I usually overcome speed limits. The risks that I take in life, I like to overcome speed limits. So if you follow me, you will also overcome these speed limits. So better don't follow me. Okay, so these are kinds of more refinement in the kinds of application that can be developed for ACC. So that's for one vehicle to another vehicle communication. That is.
Can I ask a question,
yeah.
and the chairs could declare me off topic? What's the security model here? It just seems like Lou Berger. It just seems so hackable.
So what? So
what is the what is the security model on this? It seems that it would be very easy to undermine the system. Yes, lie.
Yeah. So there is a lot of security work ongoing. Unfortunately, we don't have a security talk today, but please make the comments.
Yeah. So I'm familiar with some of the security work that's going on in this.
Name, please.
Eric Rescorla. I'm familiar with some of the security work that's going on in this. What would cause me to say I usually speed versus I usually don't speed?
Sorry, what would you call
I said, so when I ask your car, can I follow you? How would your car decide whether to say, yes, but I usually am speeding?
Because that's the driver's decision. That's the human driver that decides what answer to give. Okay, I pre-configure these answers in my dashboard, and whenever somebody asks my car if they want to follow me, I tell the car what to tell on my side.
I'm not even sure where to start with that.
No, what kind of problem do you see? I don't understand.
How much time do you have? I mean, what sane person would program their car to say that?
Well, have you ever overcome speed limits? Did you do it consciously?
Yes. So okay. So just out of curiosity, if police come up behind me and ask to follow me, should my car say yes, but I like to speed?
Well, you should know there is ongoing debate whether there is ongoing debate to decide whether to allow or not police enforcement to query a stopped car whether they have overcome or not the speed limits. Not query the driver, but query the car. That means make available a RG45 socket to the police to plug some laptop into it and query the car, not the driver. Okay, because the driver may.
Right, but again, I
There
think.
is ongoing debate about that.
I
Okay, we can have an opinion, say no, it's not good, or yes,
No.
it's very good, but.
I think you've made your point.
Yeah, I'm just trying to understand, like, this seems like, I'm familiar with designing these systems, and it seems like you're already starting to design something that is going to have some horrifying security and privacy properties, and this is like the first slide I've seen, basically.
Yeah, privacy is important, should be considered. We need somebody to do it.
Really not a good answer.
So.
This is Sandra Cespedes. I just want to make a comment about the security aspect. Just to say that there is a lot of work being done in this particular example, the CACC. There are, at least in the academia, I know for a fact that in the last 3 or 4 years, there have been papers about security for this, taking into account data fusion to actually say that what my speed I'm reporting is actually true, and other aspects of this. So there is ongoing work about this, and of course it's a very sensitive aspect because of the security part,
Yes,
safety part
safety.
of it, but there is ongoing work about this.
Yeah, so that's encouraging to hear, and if they can submit an internet draft or something on this topic, it would be wonderful.
So Eric Berger, and I was just clueless that this was going on, so I read up real fast, because we're also doing work on this, we being Georgetown. And so 2 things. One is, I will pile higher and deeper. It's not just security. There's a lot of privacy issues here. We work a lot on the security stuff of bad things happen if these messages get jammed. And so one thing I didn't see was things about how you can assure delivery is something that needs to be done, because it is possible, but you need to do it.
Yes.
It's not just a mobile IP thing.
Yeah.
I need to find the IP address of that car there. It's a lot harder than that.
Yeah, so communication jamming is an important aspect that should be considered. Depends on which layer, but yeah.
So Eric Nordmark, it's not a comment on this presentation, but there was a IETF plenary recently, and part of that actually covered more of the security aspect. So that would be a good thing for people to go back and look at, because it did seem to take these things a lot more seriously, including the issues that the purpose of this is to save lives and to some extent increase efficiency as well, right? Hence, what I took from that was that the people that are thinking about this issue say, well, you have to set legal policies in place so the police can go get that data, because then people are going to turn it off, disable that feature in your car, and you're going to lose lives and miss your purpose, right? But I think that sort of hired a bit has been missing from this, so it's useful to go look at that.
Two more minutes on the presentation.
Sorry to back up here, Eric, but I did some of the design of that system. So I'm quite familiar with the design requirements. And the design requirements are absolutely or not, we're going to like spam all this crap on the wire and then have laws saying people can't interrogate the vehicle and ask shit. So, like, yeah, I'm just saying, like, that was not the design requirement when the systems were designed.
Okay, as Carlos said, we only have 2 more minutes on this presentation, so let's at least get to the conclusion slides.
This is a scalability and interoperability discussion of IP between vehicles. There are numerous projects, at least in Europe right now, that demonstrate. I invite you to come and see a big truck that is followed by smaller trucks. It's called platooning, in which they consume less energy and they remove their hands from the wheel so they can work and sleep while being virtually being tracked by the front car. So this is currently has a certain size. It uses Wi-Fi 802.11p communication between vehicles, but has a topology model that is somehow limited in that it doesn't scale. Okay, it uses the maximum range of 802.11p, which is not very long. You cannot build 2 kilometers trains if you want, if you use 802.11p like this. Now, in the future deployments, this car, there is a problem with it, but conversion PowerPoint to PDF made it that this car has been reverted, but Normally, it's a front. It's reverse. Okay, it also follows the front car, and you may put a interface in the front and interface in the rear, and with a vehicle-to-vehicle communication one by one. IP routing has this scalability property that it could go very large. So you could think of larger platoons in the future. So, but for the moment, this is just a scalability, more like a research activity, and maybe not get deployed very soon. So we have a gap analysis. We wonder which protocols can we use in this document that I presented. Which protocols can we use to realize this vehicle-to-vehicle communication? 3 protocols have been considered: neighbor discovery, mobile IP, and ODVV2. But I have been told that there are much more protocols that need to be considered in the TCP/IP family. Okay, this is DNS, HTTP, and others, and how can they work in a V2V setting, service discovery, and so on. You will see that in the problem statement discussion. And that's all, I think. Thank you.
Thank you very much.
Okay, so thank you. So I'd like to introduce about the problem statement of the scenario in IP in vehicle-to-vehicle communication. So I'm Dapeng Liu. So I just is joined to work with Alex and Charlie Perkins. And here is the use case. I think Alex has mentioned that there is a scenario called cooperative adaptive risk control and platooning. And in that scenario, there is a requirement that there is some IP data exchange between the vehicles, and connecting these vehicles through long range, for example, using cellular network is possible, but typically incurs too many delay. So in this particular scenario, instead we prefer to use short range communication technologies, as Alex just mentioned. And the problem in this use case is that how the two vehicles to establish a direct IP communication passes between the computers on the networks embedded in the 2 or more neighboring and maybe potentially very fast moving vehicles. So that is the basic problem. And the assumption here is that inside the vehicle there is a network, and there is a Ethernet cables and run through the car and together with the CAN networks. And typically there is a one edge router, a wireless edge router, that is in charge of the wireless communications outside the car. And they may use, for example, IEEE 802.11p and or other wireless technologies. And here is a picture of the scenario. So we can see that there is car in the left, and there is another vehicle in the right. And both in the vehicles there is an edge router, and there in this picture the left vehicle has a GPS controller. We call that GPS PC, and in the right vehicle there is a braking controller. We call that braking PC. So here is a problem that the 2 edge routers need to have forwarding information. I think someone just mentioned how to exchange this forwarding information and set up the route. So that's the basic problem here. And we think we can break the problem into 2 sub-problems. The first one is how to discover the prefix, how the 2 edge routers discover it between each other. So that's the first problem. The second one is how to set up the routing information and others. So that is the prefix exchange sub-problems. So let's first look at the first problem, discovery problem. Many information we need to discover between the 2 edge routers. For example, the link layer information, the wireless link layer parameters, maybe the power of the wireless link, and also the MIC layer information that need to be discovered. And in the IP layer, the vehicles, for example, the first edge router 1 need to discover the IP address and the IP prefix of the edge router 2. And also the edge router 2 need to discover the IP address and the IP prefix of edge router 1. And also, service related information is very important because normally the controller in the vehicle doesn't know the IP address of the neighboring vehicles. Normally they will use some service related discovery mechanism to discover the service. Then they set up IP communication after that. Okay, so another problem is to set up the routing information. So I think after we discovered the two edge routers discovered between each other, the prefix exchange mechanism is needed. Otherwise, although the neighboring vehicles know the prefix of each other, they cannot set up the IP communication. So there should be a routing table mechanism to maintain the prefix and next hop IP address in the vehicles, and also need some updating if in the situations when the vehicles leave the network. So that is a dynamic routing table here. Okay, so that's the basic problem. I agree that I didn't mention here about the security and privacy issue, but I agree that that is very important aspect we need to work on. Thanks.
Questions? Okay. Can I just ask a question? You mentioned that you need to deal with a case where vehicles leave the network. What I didn't see in here is how the vehicles know the opposite case when another vehicle's entered. In other words, that they need to discover the prefix and the addresses.
Okay, I think that's a good question. So that belongs to the first problem, that how you can discover the neighboring vehicles. So so there are many ways. For example, you can use router attachment, something mechanism like that. But we believe that there should be some extension to suitable for this particular scenario. Okay.
Der Kutscher, so I think we should really characterize this use case, say, correctly. So if you think about autonomous driving, so we are using different types of sensors today, radar, laser, and so on. And in that context, it would make a lot of sense to have like a communication means to distribute like simple information, like speed of a car ahead and so on, if you can secure it correctly. But would you really say you would use that network also for exchanging service information, offering video transcoding services? I'm not really sure.
Okay, so this particular use case is mainly focused on the two neighboring vehicles to change information that's based on IP. So it could be used in other deployment scenarios also, but
sure, you can do many things over IP, but I mean, my question is, so what is in your view really realistic? I mean, what would really be useful in these scenarios? I mean, wouldn't it be rather used as a autonomous driving support system rather than an arbitrary, say, internet where you exchange all kinds of information or offer relay services and so on?
Okay, so I think in Ala's tutorial he mentioned some scenario that how this scenario is deployed or in demo in real life. As one example is we mentioned in the first slide is called cooperative adaptive cruise control and platooning.
Right.
So that's one major use case.
I mean, isn't that the main application, not the main use case?
It has some trial and demos experiment, but I think other SDOs are currently developing expecting solutions on this scenario. So it's not happened yet, but we expect it will, become real in future.
It is one use case that exposes the need for IP communication between vehicles. If you look at for example, LTE V2X specification, you will find there are multiple scenarios where a moving network needs to talk to another moving network. But we could have listed them all, but then you don't understand exactly what. So that's why we pick one, okay? And we show how IP is used in
Janet from Ericsson. You wrote here like connecting vehicles through long-range cellular networks typically incur too much delays. Do you have any data regarding that compared to the solution you're giving, or just like an hypothesis?
I personally don't have the exactly data about the delays comparisons, but that scenario.
So that's a hypothesis, not a problem. Okay, thank you.
it is a problem, okay? The delay.
Do you have any data?
Yes, you want the data? How much do you want? I mean,
sure. I mean, just one single data.
50 milliseconds, okay? A round trip time between vehicles if it goes to the cellular network, and 5 milliseconds if it goes directly vehicle to vehicle. So that's a reduction, a 10 times reduction in if you talk directly between two vehicles.
Yeah, sure. Yeah, it would be nice to see, like, back this up with the data so that we can think about it, like, right? So this is not a hypothesis. You're saying this is a problem, but yeah.
Okay, thanks. So I mean, I personally don't know the data, but I think others may know. Yes.
Hi, Randall Gellens. I just wanted to follow up. You were mentioning that this is a use case that shows why IP is needed. And so my question is, I didn't actually get from this that you're showing how IP can be used and how IP can be useful, but that's not the same as how IP is needed. And the reason I ask that is because you previously presentations mentioned that there are all these other messaging protocols and formats out there. So my question is, do we have a description somewhere of why we need IP? And I'm not asking because I'm saying we don't. I'm asking because we need to demonstrate that we do.
Okay, so actually in this presentation, we mainly focus on the problem statement. So the assumption is that we use IP. And why we use IP, I think in Alex's tutorial, he mentioned some reasons why IP is more preferred than layer 2 technologies. So, yeah.
Eric Nordmark. So I can see how things, once you sort of get to having identified the car in front of you, this is how you can start communicating and setting up IP. But if what I'm missing from a sort of identity or identifying perspective is what's that step, and have people already defined that? Basically, I want to follow that white car, right? I don't want to follow the car that's 2 lanes over there, which I might very well reach over a radio or even Li-Fi or whatever it's called. I might be able to communicate with some other car, but it's not the one I'm behind, right? And I need to securely make sure that I can go ask, what's your IP address on the previous slide, right? Well, I need to define who I am I asking? And have people already worked out those pieces somewhere else? Because that's independent whether I'm using L2 or IP or whatever, right?
Okay, so I agree with your comments that, identity and service discovery is very important problems here, and also the privacy security. So I haven't listed all of the problem here, but I agree with your comments. If people agree to work on this problem, we need to consider all those factors.
This is Hans. So I wonder from the scenarios, if I had correctly understood it, it's sort of sounds like a short-term communication, sort of like one hop typically. And I wonder whether IP is really used at the best possible extent there. Like typically, it's more beneficial if you actually have it over multiple hops, bridge potentially different link layer technologies and radio technologies. But here it seems more like the use would be like similar to a beacon. just broadcast information like I'm here, I'm using this speed. That's useful. I don't know. So I'm wondering, like, you add another layer with another set of identifiers, but you actually don't really use them. It may actually confuse more than it helps. But maybe there are other scenarios which, and I have to apologize that I'm not an expert in that field.
Okay, I think why use IP is is a big question for this whole thing. So so my personally thinking is that for example, for the Internet of Things, people can see that more and more devices currently are using IP. But previously, people think about use some link layer technology or other solutions, but not IP. But currently, we think more and more things are connected to the Internet. And for the vehicle, we believe it's the same trend. And actually, in other SDOs, I think Alex will introduce that later. They actually expecting IETF and or other organizations to develop solutions based on IP. So, my short answer is that's a trend, I believe. Okay.
This is Sandra.
Last question on. I'm sorry. Last question on this presentation, please. Thank you.
This is Sandra Cespedes. Related to the previous comment, I will imagine this same scenario where you are, instead of broadcasting something, you are streaming some video to the vehicle in front. So in that case, yeah, you go one hop communication, but you want to address that to specific vehicle in front of you, not to any neighboring vehicle. And in that case, if you're streaming video, you will want to reuse whatever is already done over TCP/IP. Okay. So in that case, you will need IP. So I see this is a very consistent problem statement for that specific scenario. And I can think of many other applications that will also need IP for that case.
Okay, that makes sense. Thanks.
Thank you very much. Next presentation is Paul. And while we prepare, has anyone not completed the blue sheet? I have one here. If the other one is, thank you. All yours.
Okay, let me start.
You have the clicker?
Oh, okay. My slide.
Keep going.
Keep going. Oh, keep going. Okay.
There you go.
Okay. Hello, everyone. My name is Paul Jung from SKKU in South Korea, Sungkyung University. My co-author is Tam Oh, professor at RIT. So the objective of this draft is to specify the problem statement for IP version 6 based V2I, vehicle to infrastructure networking. The assumption is we are using L2.11p as a MAC layer. Of course, we can use other H, Brown, or other MAC layer protocol can be used. Also, I believe IP version 6 is a right network layer protocol. And also, we are using infrastructure node. It is called RSU, roadside unit, that is connected to internet. Also, the focus of this draft is networking issues in one-hop communication rather than a multi-hop. Multi-hop communication will be considered later on. And also, the internetworking between vehicle moving network and the roadside unit, the internal network. It is called the fixed network. So this figure shows the configuration of a V2I network. So here we have a vehicular controller, a cloud. Some controller, it is called the traffic control center. It is a terminology for the ITS. And also we have a RSU1, RSU2, kind of access point for V2I scenario. Also the vehicle moving like this. So this figure shows the communication scenario. The left-hand side is the vehicle moving network, and right-hand side is the RCU or fixed network. So each of node has inside internal network, could be a multi-hop, the subnet. So the goal is you can see some host can communicate with some server, such as some navigation service or accident, some advertisement or online diagnosis, such as the vehicle has a lot of sensors inside. That sensing information can be delivered to one of the server in RSU. So RSU could be, we can say, some localized cloud. So the server can analyze online. So we can diagnose. There is something happen in vehicle. RSU, some server can notify that vehicle, also the surrounding vehicle, giving some notice, right? Prepare for some possible accident. So support such kinds of services, we need to address some issues. The first issue is IP version 6 addressing. So we can use two policies for IP addressing. The first one is local address, such as URA. The second one is we can use global IP version 6 to support some internet networking, some application inside the vehicle node, and some cloud side. The second one is the neighbor discovery. So we are assuming vehicle and RSU has the edge router or access router, some external link address. So that address should be configured, right? So in that case, we need to consider the high-speed parameters for neighbor discovery and address auto-configuration. Also, naming service. We can configure the in-vehicle devices with some DNS names. That names should be configured, auto-configured using MDNS or DNSNA. This is another MyDirect, and also that name can be auto-configured and then registered to a DNS server inside the vehicle or outside the vehicle, which means the RSU DNS server. Also, DNS name resolution service also provided. The other one is IP mobility support. To support some TCP ongoing session, we need to consider DMM could be one of the possible solutions. Also, the IP mobile IP version 6 configure can be adjusted for high speed vehicle speed to support the mobility of the vehicle devices. So the main issues are RSU of vehicle internet networking, which means inside vehicle fixed the moving network, and the RSU of fixed network, right? So in that case, the assumption is that the prefix inside the fixed or moving network assignment can be done using a prefix delegation protocol such as DHCP version 6, or we can configure using the manual pre-configuration. And then the problem that mentioned that we have 3 stages. The procedures. The first one is the discovery, exchange some communication parameters such as a MAC address or some specific link layers, a MAC protocol, file, something like that. And then prefix exchange can be done to communicate inside the vehicle node and the RSU fixed node. So, and then we can provide unicast or DNS naming services. So many people gave us some feedback. So next step for this draft is we include the requirement for prefix exchange protocol, and also we are using the same terminology from other drafts, such as V2V. The third one is current draft using site local, but as you know, this is deprecated. We are using URA. And also the complementarity for mobile IP version 6 for the ongoing TCP session, we can consider NEMO and DMN as a possible some extension. And also security is very important. So the certificate are very important, such as we are using RSU infrastructure, we can share temporarily for the certificate. So the vehicle can get certificate, and then we can verify this message from the vehicle is valid or not. So, and also privacy consideration. So the vehicle, some VIN ID is used. We can identify vehicle and the driver, so we can use the temporary identifier for the communication. Also, we we are using the ISO other standard already has terminology, try to use a unified terminology. Also, we can support the multiple net layer, such as the broadband radio access network, or the Wi-Fi, or radio infrared, something like that, as long as 5.9 DSRC 11P. So also I will address other comments from at the ITS mailing group. Okay, thank you.
Questions?
Hello, this is Charlie Perkins. I have a very small question on your last slide.
Mm-hmm. The previous?
Previous slide, yeah.
Okay.
It says a method of connecting the vehicle's moving network directly to the RSU's fixed network. What does that mean?
Say it again? Which?
The very last line. How does it mean to directly connect to the RSU?
Okay. So
the very last.
This one?
That, yes.
Okay. So, one possible solution is the vehicle moving network prefix and the RSU fixed network prefix exchanged somehow, and then they can communicate to each other. So the discovery protocol and exchange protocol is not defined yet, but we assume using some protocol we can exchange the prefixes, and then they can communicate each other. So probably the mobile ad hoc fashion style, communication can be used. Thank you. Yeah.
So I have a few questions on this draft. First, did you consider that the network may be congested? Because if you get an IPv6 header, which is very large, and a very large amount of cars, you may have hundreds of cars connected to your infrastructure.
Mm-hmm.
You may get congestion in the network and not pass any.
Okay. So one solution is you can see DSRC having 7 channels. So roadside unit allocate some channels, subset of the vehicle. Imagine one intersection, 100 vehicle moving, passing that intersection. The RSU can allocate that channel using mag layer. So allocate, and then on top of that, the channel, the IP, can be used. So we can try to separate the traffic using the multiple channels. That is one of the possible solutions.
Okay.
Yeah.
I would rather consider a reduction of the IP size packet. Things like 6 low or something like that.
You are saying that IP?
Yeah, to reduce the size of the packets and avoid the congestion.
Okay.
Because switching from channel to channel is not that easy.
Mm-hmm. Right. So that is very important. So probably we need to consider, but I don't have the solution yet. But that is a very good aspect. We need to consider that conjunction problem. Yeah.
I think this is an issue to be added. Another one would be to put some performance figures, because if you have, you should consider also the time under which you are under the coverage of your access point or RSU, considering that the car may be moving very fast. Mm-hmm. And the coverage of the RSU may not be that large. It was not the same problem when you were in V2V, but when you are in V2I, the time when you are going to connect to the infrastructure may be very short.
Right.
So I think this is a strong issue here.
Right.
You have a strong performance issue, and you should put some figures.
Mm-hmm. Right.
Okay.
Okay.
Thank you.
Yeah.
This is Dino. I'm seeing that there might be different requirements or solution spaces for V2V versus V2I. And V2V will have convergence properties that will be more aggressive, possibly, than V2I. And so I think and also following up what the previous commenter said, is the amount of congestion is going to be an issue, because lost packets here could not be very safe, right? So I think we have to be careful in not doing too much setup work, too much chit chat on the network. So I think the V2V it's pretty much a local matter, and in the V2V case, you may not have to depend on internet infrastructure to get directory naming, addressing information. But since V to I, the goal is to talk to somebody that's outside, you might want to do it. But I have a feeling I don't want to propose two different solutions for these scenarios. So I think we should focus on making V2V efficient, because we're going to be forced to, and that same mechanism used for the V to I case as well. So not only doing naming, addressing, which is a lot of chit chat, a lot of protocol signaling back and forth, but also security is going to require Diffie-Hellman exchanges and stuff. This is a lot of packets going back and forth before you can send a really important packet like break the car, right? Break not as in damage the car, but put the brake on the car.
Okay, so our plan is we try to make one solution, V2V, V2I. Yeah, that is I believe our direction. So yeah, definitely we try to use. Also, but the benefit from the V2I case, we can temporarily or easily share the certificate because of the infrastructure connected to the internet, right? So we can share. Just only B2B case, it is very hard.
If you go get a certificate, you have to go to a CA. In the V2V case, that may not be practical. That's all my point is.
Okay, this is Nabil Benamar, University of Ismail Meknes. I'm supporting the draft, and I've just done a question. I have sent you many questions and comments in the mailing list, but I would like to ask about the difference between Slack and DHCP version 6 relating to which would be quicker to get an address. You have mentioned these two, but how can you be sure about which one will be quicker and faster to get an address when we have moving cars that are fast and they don't have time to get an RA? We know that even we use the DHCP version 6, it's through a router that the node will know that its configuration should be given by a DHCP server. So how can we be sure about the fastest one?
Oh, so could you clarify your question? So you're talking about some configuration for the IP address. Could you clarify your question?
Yes, you are comparing between Slack and DHCP v6. So which one we will use in this?
Oh, so your RA or DHCP for configuration?
Yes.
So personally, I prefer the RA approach because the RCU, the route advertisement, depending on the congestion, the density of a vehicle, and then the vehicle can be easily configured. The DHCP case, we need to require additional messages, such as DHCP discovery message, also some allocation request, something like that. So I believe the RA-based approach is more efficient in terms of the congestions. Okay, thank you. Yeah.
And a quick clarification question on the use case. So what I took from your presentation is that the roadside units, they are connected to the internet. But as far as I know, mainly for being configurable by some road operator. And the actual communication between the car and the RSU is more also like a beacon kind of communication, where you just send stuff to the car, which can then be used for autonomous driving and other things. I don't think there's, or maybe you can clarify, is there really the use case that you use the roadside unit to connect to somewhere else? Is that really a use case?
Okay. So the use cases I mentioned, the major use cases for V2I is avoid the accident surrounding intersection area. So just the V2V case, certain cases, the message exchange is not promptly exchanged. So the roadside unit case can be help relay the message. For example, some vehicle moving this direction, another vehicle moving this direction, roadside unit aware of that movement, and then share advertise the position and direction information, and then we can avoid. So that is, I think, the good use case for this.
Right, but this then again also sounds like a one-hop communication between the car and the RSU.
So the other one is the RSU. We assume this is a kind of some localized cloud. It has some information for driving, navigation, or accident information. So especially some accident happen, that information is propagated to RSU. RSU also advertise one-hop range in the vehicle to avoid the further collision, something like that. So that is one possible use case.
Can I answer?
Yeah.
So a clarification with the question was whether currently deployed RSUs are connected to the internet. This is what you're showing.
Right, sure, yeah.
So you have RSU1, RSU2 that connect to the vehicular cloud and to a traffic control center, or even RSU1 connected directly to RSU2. This is what the picture shows, and this is what some deployments already do. Okay. So this is why we have the picture to express what's really out there. I can give you the address, the name of the project, and so on. So we have maybe 6 months ago, we have already experimented with RSU handovers, with RSU connected to the vehicular cloud, and RSUs managed by the TCC, the Traffic Control Center, remotely connects to RSU and does some configuration on RSU and so on. But there is also connection directly from vehicle to the TCC through the RSU. So this is something that's being deployed.
Okay, thank you, Alex. Yeah. Okay, thank you.
Thanks. Okay, the next thing on the agenda is, given this understanding of the problem statements and potential work, what kind of documents would the ITS working group, if it were chartered, produce? We'd like to hear your thoughts given that level set we just had.
Aaron Falk. So just having listened to the discussion today, it sounds like maybe some security and privacy considerations would be a useful contribution.
Yep.
Yeah, could say a plus one to that. And so what I would like to see, so we have looked a bit into a few use cases, and then I've been discussing how can IP be used for that. So I'm missing a bit the link between those. So what are the actual communication requirements? So what kind of network do we or communication paradigms do we really envision? And maybe in the second step, then figure out, okay, how can we use IP for that? I mean, I think we are pretty sure that we can use IP somehow, but we haven't really figured out, is it really the best approach, and what is really required in those scenarios?
Does that, just to be clear, does that sound like requirements? Is that what you're talking about? Or an applicability statement?
Yeah, so I would like to see like a network design that would allow us to discuss requirements. So that could be a requirements document, if you want.
So, Eric, not Mark, I'm having a bit of a hard time wrapping my head around this for the following reason. One is, basically, some people are saying that, well, for this communication pattern, for this use case, we don't have to use IP, right? And other people are saying, well, we could use IP, or IP would be beneficial. And in that world, it's hard to figure out what would the IETF do. If we basically postulate that we're going to try to use IP for this, it might be linked local IP, single hop, but it's all going to be IP. Then at least it's simpler to think about, okay, how do we do these different things, and when is it appropriate for which sort of use cases is single hop, link local communication sufficient? In which cases do you have to set up some form of routing and acquire addresses that can be used to route things for these multi-hop things? Then I think it's easier to, at least in my head, to find a path, sort of, here's the set of things we need to fill in, right? And in that world, sort of thinking about what are the use cases and the communication patterns, and what does that imply in terms of type of IP addresses you need. Do you just need ULAs? Do you just need link locals? Do you need to get globals because you're gonna use the same infrastructure to stream the movie, whatever, to the car from the internet? And see what assumptions does that place on other parts, on existing protocols in terms of the time it takes to acquire IP addresses, for instance. And do we need to check for duplicates? Are there things in our current assumptions about rather stationary networks where we would need to improve things, right? But walking through that, sort of put IP everywhere and suspend disbelief and saying maybe it's not necessary, then we can at least make some progress.
So Eric, I think it's the case that some of the work that's been done in other standards bodies is going to stand. We heard about at the beginning, some of the IEEE 1609 work, some of the ETSI work, and those are not using IP.
Yes.
And I think those are, not part of this discussion. Those things will exist in the system, but not use IP, and we must assume they're still there. And if they choose to change, it'll be those groups that change them.
Sure, but then I guess I don't understand, so what is sort of in scope if you say that? Does that mean that platooning is no longer in scope for us?
Well, we spent a few minutes here talking about things that might be better if IP was used, right?
Yes.
And so the question is...
But maybe but I don't know whether those groups have already carved off saying, no, that they're going to go solve this stuff without IP.
I think given the deployment things that some of the transportation regulators have given, they're not going to wait for us. So they will be in the environment.
Yeah. Okay.
So the question, I think, so the early part you said is that you're having a hard time getting your head around why IP, and if you use IP, how would you use it and how does it help? Maybe that's the first document.
Yeah, it could be, but...
Stan Ratliff. I'm just wondering, especially in the case of the vehicle-to-vehicle stuff, since we're talking about vehicles coming together and communicating, aren't we talking about a mobile ad hoc network? Shouldn't this be a set of use cases in MAN-A?
I think the first talk said that this is a one-hop example of that.
Just thought I'd point that out.
Eric Berger, yeah, I can't resist. It's a mobile ad hoc network. Most of the use cases I know of in the automotive space are things like, I want to talk to all the cars within 200 meters of me, or I want to talk to cars that are in my direction of travel but are closing in on me, or I want to send a message that gets propagated backwards because I'm talking about an accident that I'm seeing or something like that. And so it's getting backwards to the people who are coming to it. And none of that really seems to leverage IP. And likewise, we're going to stream movies over this. Well, no, you're going to stream movies over your LTE connection, which we've already said you're going to have anyway. So I think, that kind of fundamental question that you're hearing a lot here at the mic is, so really, why are we talking? I mean, in the IETF, every nail is an IP, needs an IP hammer. And this will be great for business, but I want to make sure we're doing, something that people won't go, ew, when we're done.
This is Dino. So let me take a different approach, maybe a more marketing approach, not what IP will do to help it, but if you don't have IP, these are the sorts of problems that could occur. So we know a lot of vehicles today already have IP in it because they want to talk, a Mercedes and a BMW can surf to www.yahoo.com and it works. So IP is already there, right? So you might as well use something. We see these cars that are pretty complex beasts with hundreds of computers in them. And we see some new manufacturers that are trying to simplify automobiles so they can get to certain price points and efficiencies. Basically, I think I think we're going to see these cars just like TV sets now where you can put applications on them. I think we're going to see cars where we're going to want to write applications. And when you write high-level applications today, most of them over over IP or IPv6, right? And I see there's going to be a time where maybe a BMW wants to talk to a Mercedes, and they're going to have a compatible format. And if you don't, we're going to have an n-squared problem at very low level, and we're going to have applications writing to these 802 standards and not writing to IP internet standards. So I think if you don't do IP, there's not going to be an open environment where we could do some really cool things peer-to-peer among different manufacturers. You would think the auto manufacturers would want something that's relatively open and still be able to differentiate however they can with other things.
My name is Bachar Sarikal.
Wait, hold on, can we go to the back mic?
Oh, okay.
Spencer Dawkins. So I was kind of waiting for this to sink to the level of a transport question. So
We're not going that high.
Eric Nordmark was asking about streaming movies and things like that. And Eric Berger was talking about doing that on and he cast addresses for Eric. But Eric Berger was talking about doing things like that just over the LTE network or things like that. And then we had the comment about hundreds of computers in the cars, which made me start wondering about what the strategy for updating those was, and whether that might be something that you could get a really interesting BitTorrent application going. Keeping in mind that I know nothing about automotive applications, but I was trying to think of things that might be close enough to each other to be interesting and potentially generate more than just a few bytes of data.
This is Hannes. I would quickly respond to Spencer about this weirdness on having many different computers, microcontrollers, embedded controllers in a car. And the reason for that is actually fairly simple, because it has cost reasons and isolation reasons. You often, if you want to implement a certain functionality like a radio technology or some other things, you want to have it under somewhat tight control of real-time performance. So it's often easier to put it on a separate microcontroller and then have a separate processor that does application layer processing. That's what these car manufacturers do as well. If you open up a Philips Hue, you see the same. They have a couple of different radio technologies in there. You will see 3 chips. One is the application, one is the IEEE 802.15.4, and the other one is another one, for example, a Wi-Fi chip that you, or a Bluetooth smart chip. And they just do that because it's easier to do. There's an easy interface to connect between these different chips. It's just a different practice. Otherwise, you would say, like, why the heck you could run everything on one general purpose operating system, but there's a timing issue, just it's cheaper.
Okay, Bernie, then Pat.
So, Hannes, so real-time communications, there is a IETF protocol for it, RTP.
I think he knows that.
Yeah. So this is a different real-time protocol. For example,
so also people said USB is different than others. This is what they said. They said IP cannot run on USB. So now you have small modules in the car all connected by USB with TCP IP on it on USB net. So also at the beginning they were saying, no, IP is too heavy or something. And now you still have it in it and it routes, it works.
No, I wasn't saying that, but I think I was trying to provide some insight into why people do that, and I think it's for convenience and cost reasons. Many of the manufacturers, different people implement different stuff. So, for example, if you buy a Bluetooth low energy chip, you get the chip, and if you buy the same chip without the Bluetooth stack on it, it's more expensive because the volume for the stuff with Bluetooth is actually so much higher, so it's cheaper. People are cost-driven, they have certain incentives, and you need to understand the incentives when you make certain proposals.
My name is Bachar Sarikal. I just want to talk about the something that is missing so far that was not discussed, I think, maybe I missed it, Alex can say. There is an existing technology, as Hannes mentioned, the cars come with computers embedded and so on, and then they have an LTE chip which provides an uplink, and then operators support this. In America, I don't know, in this country it's supported. So that computer provides Wi-Fi access to the users in the car. So I think that LTE chip can be connected to a TSN network, time-sensitive network, and real-time communication can be supported. So I haven't seen any discussion of this type of, more commercially viable technologies for vehicular communication.
Pat and Eric.
Yeah, let's see, I wanted to respond. One thing is to Spencer's comment, which wasn't what I originally got up to respond to, but I think for updates in the car, that's generally a pretty different vehicle to infrastructure case, because, I mean, there's the vehicle to infrastructure when you've got a moving vehicle and you're trying to give it updates about road condition, and so, whether it's that there's an accident up ahead, or whether it's those signs that you never can read as you go by that say, we're going to have the road closed between this and this for maintenance or whatever. That's one whole thing. There's another thing, which is when you drive it into the service bay, and I think the updates, the software updates, are going to be more either when it's parked at home or when you're in a service bay and you've got a very stable connection, either so you're not moving at that point, because you're not going to want to update your software when you're moving, unless it's like the entertainment system to download a new app to it or something. But that's a totally different world. That's probably more the LTE world. My big concern about this, though, is well, I guess I've got three concerns about making this real. One is dealing with the security problem, and that I don't want to get something that tells me to brake when I shouldn't brake, or tells me that the intersection is clear to go through when it's not clear to go through. There's all sorts of mischief, pretty dangerous mischief to do there, and to do that while meeting the time needs of the intersections coming up, and we've only got a second or so to get that message, to make sure I can trust you and get that message through, unless there's some sort of continuity as you're going along, moving from infrastructure node to infrastructure node. So whether that's really feasible and how you're going to do that, meet the security and the time constraints at the same time, that's a big concern. And now I've forgotten what the third one was. All right, well, that's two of them anyway.
Okay, Spencer, were you going to follow up to that, or is this something new?
Yeah, and that may actually stall long enough for Pat to remember what her third point was.
Okay, well, we're closing the mic lines at this point anyway.
You might still be in it. But like I say, mostly what I was pushing on a little bit at the beginning was kind of trying to understand what the volumes of data might be, and the transport characteristics that are required there. And for this, if this work goes forward, which is like what you're trying to head towards, I don't think we have to understand those questions for this work to go forward, but I would be very curious about maybe a parallel effort to look at things like that and try to understand that. So basically, what are the transport issues that are involved there? And like I said, I don't think that has to be discussed for this work to go forward, at the level it's being discussed.
Eric?
Okay. I'm deferring for a moment.
Thank you very much. Exactly. So I think a very good, say, testing question for us could be, so would in those scenarios, so V2V and car to roadside unit, would we actually need a transport protocol like TCP yes or no. So if the answer is yes, then that may be a good argument for IP. If the answer is no, then it would be maybe also interesting. And then we would be back like to Hannes, like there are a couple of really application-specific protocols that are used today, and probably for a reason, because they don't need longer communication sessions. It's just about one data unit or one beacon. That would be really interesting to find out.
So Eric Berger, so two things. One is, and to use Dino's words, a marketing thing for when we build a charter, is how to politely put in there that automakers are notoriously bad about security, and that's a reason to do the work in the IETF, is to assume, you have to assume that all the cars are corrupt, and that any protocols we do understand that and are resilient to that. And the second point is, I'm going to channel Terry Davis here. So instead of V to I, remember I to V, you know, he made the routing tables collapse with only 12,000 airplanes in the air. Imagine what's going to happen as, you know, we, you know, try to go the other way to millions of cars. A lot easier, you know, that was pre-IPv6, so there are probably a lot of things we can do, but that should be something that would be, you know, part of the work here in the IETF, is how to, because if you don't do that, then we'll just pull the plug on it. You know, operators will pull the plug on it.
Okay, next agenda item.
That's Alex. And Alex, we're gonna cut your time in half for this presentation, like
2 minutes.
if you don't mind.
Please.
Yes, I only have.
The charter part is the critical. Yeah, exactly.
Okay, so let's be quick. We have written a draft called ITS CACC SDO. It has SDO in it, and which lists these SDOs that consider CACC and platooning. So potentially any IP work done at IETF will have impact on these SDOs. Recently, this is news. It happened yesterday. Received interest from C2CCC. This stands for Car-to-Car Communication Consortium, which is a group of car manufacturers in Europe. Discussions are ongoing. We have spotted some hurdles with respect to our relationship, but we have a person who is remotely attending, and maybe in the future he will attend and explain precisely what's happening there. ITU has a number of work items that may pertain to V2V and V2I. There is a complete list here. It's been updated in March. For example, service and functional requirements of vehicle gateway platforms, communications interface between external applications and the vehicle gateway platform, and security guidelines for V2X communication systems. So this is to say that there is a number of SDOs that are interested in CACC and platooning, and that may be impacted by IP protocols if they are designed at IETF. This includes FirstNet. It's last in the list, but it's very important.
Thank you. It's Sri, next presentation.
Okay. Yeah, so I was asked to talk about the rail architectures. I think just the context, I think whatever Alex has been talking about, whatever the little device that was in the car, let's move it to, you know, no, where are we? Sorry. Yeah. So the little device that Alex was talking about, you know, if you take the same mobile router, you know, let's put it in a train. So that's the context. You know, if you look at many of the rail operators, you know, worldwide, they are working on this, you know, connected vehicle architectures. This is pretty much, you know, worldwide In the past, like 10 years back, we started with Shinkansen. They started doing this testing of, having a mobile router in every car of the train, right? Essentially, in all the paths, pretty much in every train or in every car of the train, there is, a couple of mobile routers, and these mobile routers have egress links through, like, essentially Wi-Fi or LTE, or in some cases satellite. Almost in every case, there's satellite access as well. And along the train tracks, they are deployed like Wi-Fi access points. So like every 1 mile, there is a access point with some directional antennas. And see, the idea is, if you look at the traffic patterns, from inside, there is one dominant application is, the goal is for providing IP connectivity for the users sitting inside the car. This is nothing new. I think, in the last 5 years, we have seen it probably, worldwide in many, throughout probably in every city, in bus, these kind of deployments are there. But fundamentally, I'm more interested in the backhaul architecture, essentially what it takes to support that architecture. Today, there are access points along the train tracks. That is one point, and there is a mobile router inside the train, and this router keeps flipping between a cellular connection and the Wi-Fi connection along the tracks. That is one point. And now another aspect is essentially for managing the access points inside the train. There is like a wireless LAN controller which uses like CAPWAP, kind of like some radio resource management, and for connecting to these. So it is essentially opening up like very interesting scenarios, like a tunnel in a tunnel kind of scenario where here if I can zoom into this, this is one particular car in the train. There are like 2 mobile routers, each of them with both Wi-Fi and LTE, right? See, this mobile router can connect to wireless LAN if to the access point along the train tracks, or it can connect to the access points inside the station if the train is near the station. Now, just imagine what I'm not showing it here is essentially, imagine if there's like a wireless LAN controller, and if that wireless LAN controller has like a layer 2 tunnels to these access points, then what you're seeing is in a tunnel scenario. So why this is unique to train architectures? Today, if you look at this entire IETF zone, there's an access point here, and there is like we are able to move between access points for one reason. There is on the backhaul, there is like we tunnel all of this traffic to an aggregation gateway, and it doesn't matter which access point you're connected. Your layer 2 is not changing. Your layer 2 may be changing, but from IP point of view, your layer 3 is still intact. Now, the same thing, if I try to solve the same problem using similar approach, it becomes very complex, because your aggregation gateway is outside the train, and that brings out number of practical problems. So few things here, like the specific requirements. We want the users to be able to connect to one mobile router inside the train, and if the egress links go down, we want the users to fail out a second mobile router. So that is the second point. Earlier I talked about the tunnel and tunnel scenario. Now this is about like mobility, the basic mobility. And now more interesting other things with respect to, like, if you look at most of the rail operators, like what they want is all the diagnostics information to come back to the auto manufacturer, or if it's a vehicle. But if it's a train, essentially it needs, that information needs to securely go to the vehicle maker, or whoever is administrating, whoever is managing the mechanics and other aspects. And whereas the user traffic needs to go out. So this needs a traffic segregation. Like how you realize that, how you dynamically manage all of this is a bit of a challenge. We have worked with many deployments, but there's a lot of proprietary art here, but there's no standard way to deal with this. That is so essentially the ability to build these virtual private clouds for segregating the traffic which belongs to engine data or which belongs to user data is one key thing. I think the other thing is, like, essentially if you look at most of these rail operators, they are deploying all of these IoT kind of devices, like it could be LoRa, Sigfox, or whatever. In your vehicle is full of, or the rail is full of many small sensors and those kind of devices. The goal is to really provide connectivity for those devices, so that those devices can reach the applications, right? That requires some a framework and a some management infrastructure. The other things like essentially like, a few other use cases like as the train is going in, there will be many dead spots, right? Essentially, if you look at the topology, physical topology, not every area will be able to have an, access point. There might be some hill, if the trains might be like, the curved, tracks along that, there may not be a good Wi-Fi coverage. So there will be dead spots. Now in those spots, like, essentially what we see is like all the VPN connections and bunch of these connections fail over, right? So the question is like, there are many optimizations with respect to like, how do you ensure that those TCP sessions don't fail, for a few seconds, right? How do you keep them hanging, as the router moves between these networks? So these are, some of these types of problems, whatever I presented, these are like very, very high level, but I think what I'd like to reflect is, in general, there's a lot of automation, there's a lot of IP that is getting applied in all of these rail architectures. So the number of problems and, how you solve them, somebody needs to analyze them. And there's an opportunity for IETF to insert the IETF technologies here. Here, so far, I didn't talk about any specific, protocol or anything, but in general, this requires some analysis and some detailed study. So that's all.
Right. Thank you very much, Ray. And the last presentation is on the charter proposal discussion. Alex, to lead that, and we really are short on time.
Yep. We have written a charter, but these are the two main issues. And of course, the work items. The goal is to standardize IP-based protocol for establishing direct and secure connectivity between moving networks, some of which could be fixed permanently or temporarily. The group is concerned with all situations involving moving network to nearby moving network communications. For example, vehicle to vehicle, but also a nomadic user wearing a PAN to a home net, vehicle to infrastructure, wagon to wagon, or train to intersection. These are the work items. Describe use cases for moving network to nearby moving network communications. Problem statement for same. Problem statement for moving network to infrastructure, which includes DNS, a way to convert a name into an address and vice versa. Security and privacy requirements. Solutions, which might include new protocols. IPv6 over foo, because we have seen there are specific links here. So IPv6 over 802.11p, or over visible light communications, or over 802.11ad, or IPv6 over LTE-D. And a list of research papers in the V2V domain, which specifically identify the use of IP. Not any research paper, but those who specifically identify the use of IP. This is requested by two academia partners. Okay. So, any comments?
This is Dino. Why did you include trains but not planes?
Yes, because we have a presentation on the trains. I could not get a presentation from somebody with planes, but I know there is talk also of spaceships and PAN on the astronaut talking to a spaceship. So that's also serious talk, but I don't have a presentation. But yes, it's pertinent.
So when I used to work at Cisco, we did some research with Lufthansa, and we had a use case on IP address mobility with planes. I could present it next time if you want.
Yes, that would be very interesting. Yeah.
Yeah, well, especially when you get to the next pages, my concern is this charter is not boiling the ocean, but it's boiling the planet. And
So
that
again,
if we can, it's
boiling-
very large.
Well, it's very large as use case, but it's very narrow as technology. It's moving network to moving network communications. Isn't that specific enough?
Well, actually, in a sense, it's not, because you heard all of the security and privacy concerns, which may not be necessarily needed for a lot of some of these things, but is excruciatingly needed for others. So that's what I'm saying. This, to me, this seems incredibly big, and especially when you get to your next slides, it's huge.
Big, you mean too many work items or big as scope? Both, okay, so that's why we may need to reduce the two problem statements into one.
In fact, actually, what this struck me as, it struck me more as like an area charter, not a work group charter. I'm not saying that it's a negative thing. Maybe we need a new area.
Yeah, well, no mobility area, no, that's a specific working group with a specific work item. First, requirements, use cases, problem statements, and if necessary, solution. And IPv6/4, which is an ongoing document that could be standardized here or could be taken on here or maybe in 6 months. Yes, please.
Yeah, similar concerns. It seems to me that so these two use cases, V2V and V2 infrastructure and train connectivity, are really two totally different use cases. I'm wondering, would you say that makes sense to address this together in one effort, or are there three different things?
I think it's necessary to bring them together. And I think the train use cases exhibit some pattern similar to V2V, like you have wagon to wagon and also train to intersection. And the use case could be further analyzed and
Right, but I mean, so there are many other useful functions that you could think of, like caching in the train. You could think about car LTE routers. So this is really opening up the problem space significantly, and I'm not sure whether this can be done in one working group.
so I understand there should be a refinement or a selection activity that identifies precisely what needs to be done among the large set of use cases, maybe selecting some of them.
So I think figuring out, so what we discussed before, figuring out the applicability and usefulness of IP in these mostly one-hop communication scenarios. I mean, that's one problem you could address. And like performance-enhancing gateways and all these kind of things is a whole different category of problems. And I would choose just one.
Noted. Okay, just one.
From the Jabber Room, Michael Richardson writes, the goals in this charter are too ambitious. The trust problem between moving networks is untenable today. If we can assume that there are useful certificates, then there is almost no technical work to do.
If there are certificates, there is almost no technical work to do. That's what he says. Yeah. Okay, noted.
This is Dino. So I agree with all the previous commenters that we need a lot of focus, and that usually means trimming down the list. But what I found in the IETF over the last 25 years that I've been coming here is that because it's too focused, we see fragmented designs, and we see that one solution could have worked for that one over there. And I think what we should do is look at the requirements and then have some rough solutions and see if the same solution, one solution, could work for many of these use cases. That's going to probably be a better architectural design. So even though there's a lot of work items, we could always prune things once we could get deeper into the details.
Okay.
Eric, not Mark. Yeah, I agree that we need focus, and I'm sort of trying to figure out what success looks like in this, because this reads like success is a bunch of RFCs. It might be shiny, bright RFCs, but it's not clear how that leads to actual deployment, right? So if we can figure out a place where, so if other SDOs and governments have decided what they need sort of in the immediate term, is there a problem that's a bit further out that they haven't sort of nailed down where to go, where we could say, here's a place where the IETF can go and specify how IP is used and makes the network simpler, more uniform, lower cost, whatever. Maybe it's something like multi-hop platooning, I don't know, right? I don't know the space, but something that's might be a bit more complicated, but hence actually covers a bit more of, becomes a bit more general without being boiling the ocean, but focusing on what is that in essence a single use case that's representative and useful.
Yeah, so can answer. So I presented a list of SDOs and so on, but there is one that requests one particular item from IETF to work, okay? That one is ISO TC204 and has a request on something with IPv6 between two vehicles. It's on the slides. You can download the slides. I can show it. Slide number 13. Lack of time, I could not present. It's from Thierry Ernst. I can show it here if you want. If you want to select.
Randall Gallons.
Yeah.
One thing I didn't see on that list is anything about coordination with other SDOs. For example, there's all of this IP over foo, where foos are being done by multiple different SDOs, and we've heard that some SDOs have already developed other messaging layers. So my question is, what's the roadmap for how to do that kind of coordination, and where is the use for this coming from? Is it just people on their own thinking that we need to do this to sort of compete with other messaging and then see what shakes out in the market, or is there going to be some kind of coordinated, here's what we need messaging from them?
I think, well, Russ is busy with some important email, but there is there is coordination ongoing between ISO TC204 and IETF, and there is exchange between IETF and ISO that is channeled through particular channels in which we express our advancement and they express their needs, and we have a specific request to develop a specific part of this V2V IPv6 communication, and with even a claim that if we don't do, then they will do. So they will do some IPv6 work if we do not do. Well, they are free, right? IPv6 open specification.
So you've got that with ISO.
Yes.
What about IEEE, 3GPP, et cetera?
Well, we have a
See.
3GPP person in the room. We have, yes, this is something that could be further controlled.
We're already over time, so we're going to need to cut this discussion at this point. What I'd like to very quickly say is what we're going to do from here. We're going to post the draft text for the charter. It's already there on the mail list. What I'd like to do is have a rigorous discussion of that charter, and then say roughly a month from now, hold a virtual interim to see if we have a consensus for that charter and people who are willing to do the work. If we do not get a rigorous discussion, we will not have the virtual, and we will not have a working group before Berlin. Clear? Okay, thank you. Good work, isn't it?